Okay, today we're discussing the ratio and root tests. These are two other tools for testing convergence or divergence of a series. And the ratio test involves comparing two adjacent terms of the sequence that defines the series. So let's say you have this series of 2 to the nth. And would this converge to a number or not? Well, I think you'd be pretty sure it wouldn't, because 2, 4, 8, 16, each number that comes up doubles. And so this is actually going to diverge. But when we can verify one thing here is that if each term is double the previous, 16 divided by 8 is 2. 8 divided by 4 is 2. 4 divided by 2 is 2. 2 to the n plus 1 divided by 2 to the n is even 2. And this actually tells us something about if this series would converge or not. And that what that is the ratio test, where you take the limit of this ratio, and if your number is less than 1 for a row, in this case 2 less than 1 is not true, so the series is certainly not converging, but it will diverge if 2 is greater than 1. So row greater than 1 is when row is equal to 2. It tells you that the series diverges. This is also true if you get an infinity. If you're so unlucky as to get row equals 1, then this test just didn't work for you and you have to try something else. The most difficult part of the simplification is the algebraic simplification of the ratio. If you're ever in a pinch for time, you could use the tools, the online solvers, but it's good to try doing it yourself. I imagine that most of you out there can do this because you would have had a background in algebra before coming into calculus. So here's our first example, 2 to the nth power divided by n factorial, this series. Would this converge to a value or diverge? Just as I'll tell you my suspicion is, I don't remember the answer, but I'm suspecting it will converge because n factorial grows very, very rapidly. And so that's just my suspicion. We'll see if my hunch is correct. First, we have a definition of 0 factorial equals 1. So we do not have a division by 0. So let's look down here. So we can actually take two terms of the series by just comparing the two formulas with each other. And you can actually view this as two separate limits if it's convenient, or if it isn't, you can combine them. You can keep them as a single limit. And this would actually simplify into the product of the reciprocal by when you divide two rational functions. And so there is some simplification that can be done right away. We just saw 2 to the n plus 1 divided by 2n is equal to 2. So actually all this can simplify away. And this limit here is a little bit more involved. You might need to look at some identities to see that. So this is basically where we're at. And it turns out that n factorial over n plus 1 factorial is equal to 1 over n plus 1. You don't necessarily have to know this rule because the 2 here is just a multiplier. And what you notice here is that this denominator is going to grow much more rapidly than the numerator because the factorial function has very high growth. So this n plus 1, as n becomes larger towards infinity, this denominator is going to also approach infinity, much more so than a numerator. So this ratio is going to end up being 0 because the denominator will grow much more rapidly than a numerator. And which is why when you have a large denominator, you end up having a limit that's equal 0. And so looking back at our table for these, a limit of 0, the boundary condition is at rho equals 1. So this is 0. And so that which means that this series would in fact converge. My guess was correct. And so we have our next example. This is similar to one in the book, except I flipped it around. I took the reciprocal of it. N to the nth power over n factorial. And starting at n equals 1 this time, just because I felt like it. So we form these entire ratios in n plus 1 of each of these n's divided by the function as it's unchanged. I turn it into a product of the reciprocal. And so we have our simplification we did before has occurred again. And now the n plus 1 and n plus 1 to the n plus 1 power, you have this. You have this 1 over n to the n. So yeah, there's oh, this slide is in here twice. So we have some simplifications we can do here, such as this n plus 1 being the same base. We can reduce it by 1, because after all, this is n plus 1 to the minus 1 power in the denominator, and you have plus 1 here. So this actually reduces to just n power. And not much you can do about this n to the n. You can, and it doesn't matter to know exactly what number this converges to, just as long as you know it converges to something. The numerator is going to have slightly larger growth than the denominator in this case, but not by much. 2.78, which is approximately what this is equal to, this limit, is greater than 1, so the series diverges. And to calculate this value, you can use I used a numerical solver to approximate that, which is fair. But we have a numerator that's growing much more rapidly, growing more rapidly than the denominator, so it's not immediately obvious if it converges or not. So some of these can be a little bit tricky to solve, particularly with the limits. There's another type of test. We're running to the end of these convergence tests, and this is the root test. The root test is one of the more difficult ones because it often involves, well, taking roots to the nth power, and so that can be a little bit overwhelming at times for some people, but it's not too bad. You can recognize the situations with the root test when you see exponents with the nth power in them, like this one. This can actually be, we can actually do this with a root test as well. And I'll show you how this actually works. We have, if you have your function that describes your series, that's a sub n, if you take the nth root of that and it simplifies to a value such as rho, this value of rho, as you take this limit, whether it's less than 1 or greater than 1, can tell you if it converges or diverges. But again, just like the previous one, if it's equal to 1, the test is not of any help to you at all, because that means it's inconclusive. It could converge or it could diverge, and you wouldn't really be able to tell which way it is. So here's one example, n squared over 2 to the nth power, as n goes from 1 to infinity. We'd apply the root test by taking the nth root of the function. And when you take the nth root of a ratio, it's actually valid to split that up into to two parts, where you have the nth root of the numerator and the nth root of the denominator. You can treat those independently of each other. And it turns out in the denominator, the nth root of 2 to the nth power cancels out to 2. And so now we're left with this nth root of the n squared. And it turns out that that's a limit that you can actually look up. Nth root to the value n is equal to 1 as n approaches infinity. The difference is that we have this squared in here. And so basically what we have here is n squared to the 1/2 power. And it doesn't really matter which way you you do this. You can just as well take this into the 1/2 to the squared. And now you have this limit of n squared of n that's equal to 1. And it's squared, but it doesn't really matter. And this limit makes this limit altogether be equal to 1/2, which is less than 1. So the series will converge. We have this example here, from 1 to infinity, the summation of 1 over 1 plus n to the nth power. This one is a little bit more obvious that it's a root test. Whenever you see an n in an exponent like this one, or like here, that's like a sign that means this is going to be a root test problem. So whenever you see an n in an exponent, look towards using the root test. That's a hint to what you should be doing. And so we apply this, and then this reduces to a limit of, as n approaches infinity, 1 over 1 plus n, which this limit is equal to 0. 0 is less than 1, so from our table up here, n is less than 1, means the series converges. So it does converge. And here's our last example. Example E is 2 to the nth power over n squared. You see this n in the exponent means that we are going to be doing the root test, or at least that would be the most straightforward approach to be testing for convergence. So you take the nth root of this ratio, and you end up the numerator that turns into to 2. And the denominator, the limit as n approaches infinity of the denominator is equal to 1 once again. So you end with 2 over 1. So this 2 over 1 is 2. A row value of equal to 2 means that you have divergence. So such a series is 2 to the n over n squared, like this one here, diverges to infinity. So that's how the root test works. We'll go over the homework problems in class and get you prepared for doing those. So have fun. I'll see you in class.